Welcome to our historical webinar all about the SOM. I'm your host, Desiree, and I'm the marketing coordinator at Phytec. I've been with the company for nearly 4 years and I'm responsible for all things marketing here. So needless to say, I'm super pumped for this webinar and to introduce you to our exciting presenter, Managing Director of Phytec America, Thomas Walker. Tom got his start at Phytec in the early 90s and established our presence in the US by becoming Phytec America's very first and only employee, building our company from the ground up. What started off as an American branch of distribution for our headquarters in Mainz, Germany, is now a successful standalone Phytec entity with employees of its own and offices in downtown Seattle and Bainbridge Island, where Tom resides. He's quite literally an expert on the evolution of the system on module because he's seen it with his own eyes and been a part of its transformation over the last 25 years. I know today's presentation will be a fun trip back in time as well as an educational one. So without further ado, Thomas Walker, everyone.
Thank you, Des, and thank you everyone for joining over the internet this afternoon to partake in our webinar. As Des stated in her rousing introduction, I'm Tom Walker, Managing Director of Phytec America. I was employee number one, dating all the way back to year number one of our operations in 1996. That was the year that our parent company in Germany set up shop on these shores 10 years after its founding in 1986. And for the next 30 or so minutes, this is our agenda. We're first going to contemplate what is a system on module and ponder the board level symbiosis of system on modules with embedded chips. Then it's going to get real interesting as we're going to take a trip in the Wayback Machine to 1996, and we'll move forward through eras of embedded chips and applications. At the very end, we'll take a little sidebar about ARM and the significance of ARM in the evolution of modern embedded products. And we'll wrap up by looking at timeless design rules to which Phytec adheres despite all the rapid change that we've seen in the embedded marketplace. And then we'll take a little look at general advantages of a SOM, and then we'll go into a Q&A. First of all, what is a system on module? We like to think of it as taking common circuitry found in embedded devices and just modularizing it. What I thought we'd do now is we'll take a look inside a couple of ubiquitous embedded devices and see what sort of circuitry is located in these devices. Here we're taking a look at a Linksys router. There's the processor, RAM memory, some power circuitry, I/O devices. Here is the Xbox 360/80, very similar, same type of circuitry on the Xbox. And here we progress onto a more complex device, the iPhone 10, looking at a teardown into it. What we do with a system on module at Phytec is we take this common circuitry found in embedded devices and we integrate this circuitry into a small form factor that serves as a drop-in CPU engine that end customers can then take to expedite design of end products. Here we see the microprocessor on this representative system on module, a couple of RAM chips, flash device or flash devices, power circuitry, I/O devices. And in a system on module, we're breaking all of these features and functionality from the SOM out to board level connectors that enable interfacing or mating of our SOM into target applications. Now we're going to hop into the Wayback Machine. Get a little assistance here with Sherman and Peabody. We're going to leave this kind of terrible year 2020, and with the flick of a switch, we're going to travel back to 1996, Phytec America's first year of operations. 1996. What was it like in 1996? Bill Clinton, he was president. There was this new search engine called Google that provided an alternate to using Alta Vista or Ask Jeeves. Beavis and Butthead, they did America. The Motorola StarTAC was the top selling cellular phone in the year. Jagged Little Pill, top-selling album, back when we still had physical media. Palm launched the Palm Pilot, the precursor to smartphones and the first personal data assistant. And perhaps most significantly of all, Phytec launched the Mini Module 167, one of our early precursors to our current 5-core system on module family. We're still in 1996, and we're going to look forward at certain waypoints in the 25 years since 1996 up to where we currently are. We're starting again with the C167 device that we just looked at. That came to market in 1994. At the time, it was a Siemens device. Siemens is since known as Infineon. And what we're doing here is we're plotting these devices that we're going to look at on a scatter diagram, where that y-axis, the vertical axis, that's measuring processor speed, and the horizontal x-axis is measuring chip pin count, which gives a rough estimation as to features and functionality of these chips. Looking again at the C167, it clocked in at a mighty 20 megahertz and brought out 144 pins. One other major embedded chip that has been of importance to Phytec in the past 25 years was the Intel, now Marvell, PXA270. This was one of our first ARM-based devices, a strong ARM offshoot of the standard ARM architecture. We see here a significant increase in processor speed from the 20 megahertz up to 520 megahertz. And this device is breaking out about triple the functionality compared to its 16-bit counterpart from 1994. Jumping ahead to another era, we're now in 2011. Our next waypoint is the Texas Instruments OMAP 4460. This is based on an ARM Cortex-A9 core, comes in at a blazing 1.5 gigahertz, and we see that there's been a significant increase in the pinout, showing packing in of every more functionality and features within what's actually a considerably smaller device than these two other devices that we're looking at. Now we'll jump into the current era, 1920. What we're looking at for this era is the NXP IMX8 family processors. It is a family, so there's various processors within this group. The superset is the IMX8M Quad Max. It has 1,313 pins, quad Cortex A72 cores, dual Cortex A53 cores, which run at 1.6 and 1.2 gigahertz. And just interesting to look over this 25-year horizon, how we've gone from a fairly elemental 16-bit microcontroller breaking out 144 pins. We're looking here at a pinout of the leads of the device that align all four sides of the chip. And in 2020, there's pretty much tenfold the amount of I/O from the processor that's broken out. And the chip itself, it runs at approximately 80 times the speed of its 16-bit predecessor from 25 years ago. Now we'll walk step by step through what Phytec identifies to be 4 eras of embedded technology in the past 25 years. From our experience, we consider 1996 to 2005 to be kind of the 16-bit basic embedded era. At the end of this era, there was the segue into more ARM-based applications that we'll see in a moment. But for Phytec, 1996 to 2005 was primarily a 16-bit era that followed a 1986 to 1996 8-bit era in embedded processors. We'll take a closer look now in this era of basic embedded at the Siemens Infineon C167. As stated, 16-bit device, 20 megahertz speed, pinout 144 in a quad flat pack. The I/O functionality on this device was rather rudimentary. Address lines, data lines, serial interfaces, primarily RS-232 and CAN, controller area networking. The fact that this device is fairly rudimentary is also reflected in the fact that the number of pages in the manual technical reference manual for the C167 only needed 464 pages to describe the device. Here is the Phytec mini module 167 that we've previously seen. That is populated with the C167. In terms of software at the time was primarily taking a standard compiler such as Kyle, AR, or Tasking, and using the compiler to generate machine-readable code for download to the flash devices on the modules. The primary I/O was controller area networking, CAN, and other serial interfaces such as RS-232 and RS-485. This module is breaking out all of the controller features and other circuitry features on the board to press through pins that we see aligning three edges of the module. Some representative applications from back in this era, primarily industrial and automotive. There in the lower right corner, we see an engine control unit from Audi. We see two of the 167 devices populating that engine control unit. Up above in the yellow housing, we see an I/O control unit from Fanuc, and we also see a voltage controlled oscillator device there as representative application. So this era, what Phytec considers to be basic embedded era, very deep embedded, heavy industrial. Here is a representative Phytec or application in which a Phytec system on module, again our mini module 167, is implemented. This is an electrostatic precipitator pollution control system, which actually solidifies impurities and pollution in the air. This was launched way back in 1996. This happens to be the longest continuously produced product for which Phytec is still shipping a module. So that mini module 167 from 1996, we're still shipping it. It's being implemented in this product. Some comments as to the application, again, it's using the Infineon 167. Resources from the chip that are being used, data lines, address lines. It's using code developed with the compiler, downloaded to the flash. And one comment as to the carrier board in which our system on module is mounted, you'll see a lot of old through-hole parts. Capacitors, resistors, LEDs. So obviously this is a product from a bygone era of embedded product development, but very interesting that this is still shipping today and showing the longevity of a lot of this older technology. So we'll hop in the Wayback Machine again, and we'll go forward to this next era of embedded technology and applications. Phytec considers this to be the 32-bit era, the rise of ARM. Here we're looking again at the PXA270 device from Intel, now Marvell, which serves as our waypoint for this particular era of embedded technology. As stated, it is the X-scale offshoot of an ARM architecture. 360 pins break out to a bolt grid array there on the underside of the chip. Some of the main I/O features at the time: display, USB, MMC, and SDIO. This distinguishes itself from the previous era, where it was primarily just address lines and data lines that were breaking out from the controller at that time. Now we're talking processors. Now we're starting to see standard interfaces such as USB and Ethernet being integrated onto chips. One indicator as to the increased complexity of this device in comparison to the 16-bit device that we previously looked at is that there were 1,246 pages in the manual. Now we take a look at the 5-core PXA270 supporting this X-scale device. One other big differentiator is that the 32-bit world ushered in the era of memory management units on chip. That enabled these devices to support full-blown embedded operating systems such as Windows Embedded and Linux. I/O A lot of the capability that was on the chip at that time still needed transceivers and physical PHYs. That's the type of circuitry that Phytec would populate onto our modules here. So even though there was USB OTG on the PX8270, our module is populated with USB PHYs. Likewise, there was not Ethernet rolled into the PX8270. So Phytec populated our SOM with a standalone Ethernet controller as well as a PHY. And that's how we added this type of functionality, this much more common to what we see nowadays. The PX8270 at the time was very much targeting mobile devices. Here on the right, we see a couple of examples of that. We see some very early attempts at, I guess, smartphones. We see a Motorola device there, a Casio device, these little chiclet-like keyboards. Hard to imagine that in 2007, the first iPhone came out and pretty much supplanted this type of technology. Some of you might also remember dedicated navigation devices. We see an example of that there in the lower right corner. And there was still some industrial usage going on of the PX8270. Here we see a WinPack 8448 IO PLC control unit. This actually ran Windows embedded, despite the fact that it is a fairly deeper industrial embedded application. But overall, the PX8270 was more targeting mobile applications. Now we'll take a look at a specific example of an application running on the Phi-Core PX8270 system on module from Phytec. This is a non-invasive bladder scanner. The image that we're using here doesn't include the wand, but what this device enables is detection of contents of a bladder, launched in 2006. Current lifespan of the product is in decline, but still had a very long 10, 15-year lifespan in mass production. Comments as to what resources of the chip were utilized here. There's obviously HMI, human machine interface, going on there with the LCD. SPI peripherals play a role in interfacing the SOM to the circuitry on the carrier board that we see there. Windows CE 6.0 R2 was the operating system running on this product, and the carrier board is populated with an FPGA that also added some of the functionality to this end application. Obviously here the vertical is a medical application. And let's hop back into that Wayback Machine and proceed to the next era of embedded technology. Here at Phytec, we consider that to be the ubiquity of ARM. We have the rise of ARM, and pretty much starting the beginning of this past decade, ARM became ubiquitous across mobile and industrial applications. The device that we're looking at in particular is our waypoint for this era, is the Texas Instruments OMAP 4460 device, based on an ARM Cortex A9 IP core, is indicated previously, clocking in at 1.5 gigahertz, 547 pins in a ball grid array package. This device is also in a POP package on package, where a DDR device actually sits on top of the OMAP4 processor like a Russian stacking doll. One reason for that is to try to save PCB space by having stacking components instead of components needing to sit next to each other on PCB real estate. That's obviously to advance miniaturization technology in mobile devices. Some of the main I/O capabilities and features of the OMAP 4460 was HDMI, USB, eMMC, SD, SDIO. The complexity of this device is such that almost 6,000 pages were required in the technical reference manual to describe it. And this is the Phi-Core OMAP 4460 system on module that's populated with this TI device. In terms of software, we're again running Windows embedded and Linux on this device, Android as well. I think the main value that Phytec was providing at this time was the complexity of populating fine-pitched BGA devices in pop packaging on a printed circuit board assembly. There were a lot of thermal issues, power over hour issues, and even production issues that challenged a lot of other companies. Phytec was able to master those challenges, and we did a very solid job with our system on module design supporting this high-end, particularly for the time, OMAP 4460 device. The vertical that it primarily targeted was mobile, or is mobile. Here we see a couple of examples of devices that run on the OMAP 4460. Those include one of the original Amazon Kindle Fires, the BlackBerry Playbook, and the Barnes & Noble Nook. And some of you might still have a Google Glass at home. That was another application that ran on the OMAP 4460. As to a Phytec application example, our Phycore OMAP 4460 was designed into a handheld XRF, or X-ray fluorescent scanner. This device can detect 88% of the elements in the periodic table, so it's utilized for detecting metals for geological purposes, for RoHS compliance for electronic devices, even some homeland security applications. This product was launched in 2012, still ongoing, but also starting to see a lifespan decline. Some comments as to how the processor, the OMAP 4460, was utilized. You see here that there is a HMI display on this handheld device, so our module and the processor is driving LCD. There's also a camera and X-ray tubes that are being driven by the 4460 processor in our SOM. Another very important aspect of this application is the power management. That was all accounted for on the Phytec system on module. For this particular application as well, Phytec designed the carrier board on which the Phycore module is mounted. We see that kind of funky shaped board that was obviously required to fit into the physical form factor, the 3D housing of the gun itself. We populated the carrier board with Wi-Fi and Bluetooth devices, an accelerometer, and we took the drivers that were required for these devices and rolled them into the Windows Embedded Compact 7 and a previous Windows CE6 board support package that Phytec provided for this particular application. And here the vertical is test and measurement, but obviously merging in together with mobile. And now we'll take one last stop, ducking again into the Wayback Machine to come back to 2020. And our waypoint for this current era of embedded technology, which Phytec sees as 32 and 64-bit ARMS application processors, is the NXP IMX8 family. We'll take a look here at the family. There are numerous members of the IMX8 series family. They're based on kind of a mix and match collection of Cortex A53 and A72 processor cores. Speeds run up to 1.8 gigahertz, and the pinout of these devices ranges greatly. The subset, the IMX8M Mini and the IMX8M Nano, that is in a 486-pin ball grid array package. And the high-end device, the IMX8 Quad Max that we looked at in our chart, that has 1,313 pins that are likewise broken out to ball grid arrays on the underside of the chip. Another indicator of the complexity of these devices is the number of pages required in the technical reference manual to describe these devices. Even the subset IMX8M Mini requires over 4,000 pages, and the superset IMX8 Quad Max requires almost 10,000 pages to describe the features of that particular chip. Because these chips differ greatly from one another, Phytec has dedicated system on modules to support each primary member of the IMX8 chip family. Here we're taking a look at two of these system on modules. The one on the left is the Phycore IMX8M Mini, supporting the like-named chip from NXP. The larger module on the right is the IMX8 Quad Max, supporting the much larger device, the 8 Quad Max seen there in the silver packaging. Software that runs on these devices, Linux, Android, other operating systems such as QNX. I/O, there's very rich I/O on these devices, display, Ethernet, USB, PCI Express, MMC, SD interfaces, various interfaces for camera capabilities such as MIPI and CSI. The interesting aspect about the verticals is that this is where we're starting to see a convergence among what previously were more dedicated vertical markets. Here we're seeing the convergence of automotive, enterprise, media, mobile. Because these chips and these SOMs in support of these chips are so new, we don't have any cool examples to show quite yet, but this picture there on the right is illustrative of the convergence. We see automotive, we see navigation, we see ADAS, assisted driving. So that's the type of applications that these new processors and the SOMs that support these processors are targeting. And because we don't have an existing design win or application based on the IMX8 to show, we're going to take a step backwards to the IMX6 precursor to the IMX8. This is an application in which a Phytec system on module, our Phycore IMX6UL, has been deployed. This application is also indicative of the convergence that we're seeing. We're seeing a transportation and an IoT need merge here. This is an IoT cargo sensor device. This device is actually built into trucks, into the the big long things that attach behind a truck. My brain misses the word for that. But getting back to the application, this was launched in 2008, still an ongoing application. Some of the main MPU features used in the application is camera, low power characteristics. This is being driven on a battery. Price point was also important because these are one-way devices. They're manufactured, they're implemented into trucks, and they're used to track location as well as contents of trucks. And the device is price pointed such that it's not retrieved once the device no longer has battery power. The carrier board that supports the SOM, some of the circuitry on it, camera sensors, time of flight sensory, and very advanced power circuitry. And so we end our overview of what Phytec considers to be 4 main eras in the past quarter century of embedded technology. And we'll also take a quick look at ARM. Interesting here to note that back in 1997, 1 year after Phytec America was first founded, at that time ARM had 26 licensees. ARM is a little bit like a system on module manufacturer in a way, where it provides the IP core for processors that it then licenses to companies such as Texas Instruments and NXP. Those chip manufacturers then place additional IP and functionality around the IP core provided by ARM, similar to how a Phytec system on module provides a portable CPU core. ARM has done the design of the processor core and licenses that out to a multitude of chip manufacturers. Back in 1997, there were 26 of those. There were only 9 million ARM-based chips that shipped in 1997. Let's jump all the way into 2016, the first year of the beginning of what we consider to be the modern, current era of embedded technology. Over 1,500 licensees compared to 26 a quarter century ago. Shipments of ARM-based devices as of 2016, 17.7 billion. So we see the predominance of ARM in the embedded market. That's one reason why in this webinar we're not talking too much about x86 or other devices, but ARM characterizes a lot of the modern embedded in mobile market and technology. Now we'll do a quick look at what we consider at Phytec to be timeless design rules. Yes, there's been a lot of rapid change in embedded technology that we've just taken a look at in the past 25 years. However, at Phytec, we abide by timeless design rules ever since 1999, when we first brought out our initial Phi-Core system on module product offering. I'll quickly go through these design rules. At some point in the future, we'll have a separate webinar about these to go into greater detail. But one of our basis design rules is achieving optimal high mix and mixed speed design and signal integrity. Ways that we do that is selection of our PCB base material, frequency control devices with very tight timing characteristics. We're always using multi-layer PCBs for our system on modules, typically around 12 layers. Here we see a cross-cut of a 12-layer PCB. We're also optimally selecting components and placing and grouping those components in layouts, and selecting the components on the basis of sufficient voltages, current, and temperature margins. Another key to Phytec's timeless design rules is our adherence to achieving miniature board size. This is done by using very small footprinted components. Back when I first got involved at Phytec, we were using 0805 passives. Now we're typically using 0201, soon to be migrating to even smaller footprinted devices. We've seen a lot of the chips that populate Phytec's boards, the processors, are in BGA form factor. We also will utilize a package on package, some dual die devices, and also we're going vertically with some of our circuitry with laser drilled micro vias. Another elemental design rule for Phytec is to achieve low EMI design. We achieve this by tying 20% of all the pins that break out from our system on modules to ground. That's very important to minimize current loop areas. We're also utilizing solid ground and power planes. We talked about the multiple layer PCBs. For every power rail and for ground, there's a separate PCB layer. We're also using bypass capacitor grids in proximity to chips to likewise drive any external interference to ground quite quickly. And achieving smaller board size also means shorter signal traces, which likewise minimizes susceptibility to external noise interference. Whoops. One other design rule is the robust interconnects that we use on Phytec boards. We're typically using Samtec and Molex connectors that are compliant and tested according to IEC 668 shock and vibration tests. These board-to-board connectors also have SMT tails for strong solder fillets, friction locking for added mating retention. They're also very impervious to oxidation and dust, and they allow for multiple mating cycles, which is very helpful when you're developing with a system on module. It can then accompany an end product developer from development to prototype, even into volume production. Phytec has also started to support our SOMs in a direct solder connect, where we forego the board-to-board connector and instead use solder points to solder our SOMs down to target hardware. This is particularly advantageous for lower cost point processors. It then enables end users and Phytec to forgo the cost of board-to-board mating connectors. And one final aspect of Phytec's design rules is that we're always using industrial rated components whenever possible, -40 to +125 or -70 to +125 degrees Celsius to best enable deployment of Phytec SOMs across a wide range of use cases. The end result of these timeless design rules is a system on module that Phytec thinks delivers an optimized combination of two contrarian objectives. Number one, maximizing the features that we provide and break out at the system on module external connectors, and we're also achieving minimal size. On top of that, we're delivering a very EMI optimized design, in large part driven by the fact that we're tying 20% of all pins to ground. This enables a very EMI resistant board, and a board system on module that is also low in its own emissions. And before wrapping up, we'll take a quick look at general advantages of using a system on module. A system on module is pretty much portable CPU core, as we saw when comparing a SOM to standard embedded products. We're just modularizing the common features that are seen in embedded circuitry. What a SOM provides is a drop-in portable CPU core. End users can then evaluate on a development kit. They can develop around the SOM on the development kit. They can take the SOM, port it into prototype units of their end product, and also include the SOM in mass production. Another main benefit of Phytec system on modules is the fact that we provide rich board support packages for Linux, for Android, in support of our system on modules. These derive from the chipmaker BSPs. They're based on long-term stable kernels, and our board support packages roll in drivers that are needed for the circuitry that populate our SOMs. And we also do annual maintenance releases of our BSPs. Another advantage to using a SOM is reducing design risk. We have pre-vetted hardware. We've done layout, verification, test. We have robust BSPs. So end product developers can forego redeveloping the wheel that Phytec has already invented or other SOM makers have already invented, and simply use an off-shelf system on module instead. In many instances, an off-shelf module will also reduce cost. There's always a make-or-buy comparison. Obviously, if you're shipping a router in the millions of units, you're going to be doing a so-called chip-down design into a PCB, but for annual volumes of even below $100,000, it's often more advantageous to use a SOM and to outsource that circuitry development to Phytec, the BSP maintenance to Phytec. There's also the opportunity cost consideration that an end product developer is able to then concentrate on its expertise and leave the CPU circuitry to Phytec or another SOM manufacturer. And a final general advantage is long-term availability. As we saw, Phytec has a mini module 167 that we're still shipping 25 years later. We do product lifecycle management and maintenance of our products. We will also assist end customers in migrating from a current SOM platform to a next generation SOM platform so that their products stay timely in meeting the needs of their end markets. And one last point I'd like to cite is, at least for Phytec, we're proud of the phenomenal reliability of our system on modules. Taking a look at that OMAP 4 Phycore example, the largest shipping configuration of that, we've shipped almost 300,000 units in about a 5-year time frame, and both our production yield and our field yield are well over 99%. So that's another consideration for using a system on module, is being able to rely on the high quality that a system on module provider delivers in the form of their products. And we'll just quickly look as well, we'll kind of recap the chip scatter chart that we looked at the beginning of the webinar. Instead, here we're looking at the Phytec system on modules. We see our mini module 167 in the lower left corner. We Phycore-emphasized our 167 board level support with the Phycore 167 in 2000. These plot pretty much similarly to the chips. Again, we're looking at the processor speed on the vertical y-axis. Now we're looking at the SOM pin count, not the chip pin count, on the horizontal x-axis. And that's just showing how Phytec has likewise been able to pack in more features and functionality over the past 25 years that we've looked at our system on module level product. Then I throw in here for good measure the IMX8M Mini, which is the subset to the IMX8 Quad Max that we see there in the upper right-hand corner. And at this point, we'll turn it over or turn it back to Des. And oh, I see we forgot to turn off the Wayback Machine because we're suddenly in 1996 again. That's kind of weird, but back to you, Des, and you can wrap things up and moderate our Q&A.
Thanks, Tom. That was great. And yeah, we went a little over 30 minutes that we allotted, so I'm going to try to get through this Q&A quickly. I have just a couple of questions for you. All right. Do Phytec SOMs follow a standard pinout like SMARC or Q7?
They do not. We have dabbled in a standard form factor in pinout before, but we see that, at least for our purposes and our customer purposes, is more of a constraint. One thing that we saw in looking at our timeline is that we've gone from 144 pin devices, the C167, up to thousands of pins. A lot of these standard form factors adhere to a predefined number of pins. I think SMARC, 314 pins. Q7 is another common form factor, 230 pins, I believe. So that could become a constraint then if you're supporting a device on a system on module that adds more and more features with each evolution. Then you have to come up with a derivation of your standard form factor. The fact that we are designing the pinout of our SOMs always to maximize the capability and functionality of the processor or microcontroller that populate our SOM. And if you look back at the previous slide, you'll see that many Phytec system on modules have an external pinout that well exceeds the 314 or the 230 pin predefined pinout of the two standard form factors that I mentioned.
Okay, next question. Does Phytec assist with migration to newer system on modules?
We do, yes. I guess one advantage of a standard form factor is that there is more seamless migratability, but at the same time, it's limited by the fact that you can often overrun what the capabilities are of the standard form factor. What we do at Phytec instead is that we try to engage in a partnership relationship with our end customers, where we're speaking with them about their roadmaps. At the same time, we're in very close contact with our chip partners, NXP, Texas Instruments. We're getting early access to their roadmap information. We're an alpha partner getting early access to their chips. So that enables us to, in some instances, even design in mind for customers. Sometimes we'll even do a custom board if the situation warrants that. But yeah, we take more of a partnership, close communication approach, both with our chip partners and our customers. As seen, a lot of our end customers have products that typically have maybe a 5 to 7 year lifespan, often more. And that often gives us suitable amount of time to engage with our end customers to work with them as to future solutions and migrating to newer platforms.
Okay. And then we have time for one more question, and you kind of touched on this towards the end of your presentation, but maybe you can reiterate for us. How does Phytec achieve an almost 20-year longevity on their products?
Well, we have a very, very good purchasing department. If we think back to that XR fluorescence or XRF fluorescence gun, which I happen to have here, by the way, we've actually done, I think, 6 last time buys with that particular customer. So we're very good at selecting components that, number one, are going to be there in 2 to 3 years. They're not short-lived components. I know now with so much of technology being driven by cell phone and mobile markets, a lot of these devices, memory in particular, might have a 2 to 3 year lifespan. So we're very judicious in the components we select. It's not only silicon vendor or the microprocessor manufacturers that we have close relationships with. We have very close relationships with memory manufacturers as well. We're looking at future roadmaps. We do an excellent job of finding impossible chips that have been EOL for X amount of years. So yeah, those are some of the things that Phytec does to sustain our product. Number one, we're very proactive in what we select. Number two, when we have to be reactive, we have a very good network to do so and are typically able to sustain products for quite a long time.
Okay. Well, that's going to conclude our Q&A for today. Thank you all for attending. If we didn't get to your question, we'll contact you directly after the webinar, or if there's any others that come up, you can always email us at marketing@phytec.com, and we will follow up with you. We'll be sending a recap newsletter shortly containing the slides and a link to a feedback survey. And then you'll also be prompted with the feedback survey upon exiting the webinar. So we would really appreciate you filling it out so that we can continue to improve. And then also look forward to seeing our webinar recording on our YouTube channel, probably posted next week. So thanks again, and we will see you all next time.